Hello, everyone. As Giovanni said, today I'll be talking about the quantitative evaluation of dynamic platform techniques that we have done in this project. Now, I would like to start by a motivating example as to why people and researchers develop these dynamic platform techniques. Back in April, there was a severe zero-day vulnerability that was discovered in Internet Explorer. And as it turned out, versions 6 through 11 of Internet Explorer were vulnerable to this vulnerability. And the vulnerability was so severe that it allowed remote code execution in IE. And the problem was so large that the Department of Homeland Security actually recommended that people stop using IE until this was fixed. Now, if you look at some of the statistics, around 2.8 billion internet users exist in the world. And at that time, roughly 17% of them were using those versions of IE. So that boils down to more than 400 million users. This is a very big problem. We have a vulnerability that an attacker can exploit that can impact hundreds of millions of users at once. So we have, because of homogeneous systems that we have created economy of scale for the attacker. They can develop one thing and exploit a lot of machines. So this was the motivation behind an area that's called moving target techniques. And these are techniques that try to make systems more diverse, randomized systems, or somehow dynamically change configurations of systems in order to make them less vulnerable to these large-scale exploits. And there are generally 5 large domains of moving target techniques. The first one is dynamic data, which dynamically changes data syntax or format on the fly. The next one is dynamic software techniques. These are techniques that diversify the software applications. We have dynamic runtime environment techniques that change the execution context of an application, things like memory randomization, instruction set randomization. Then we have dynamic platform techniques, which is the focus of this talk. These are techniques that change the properties of the platform, which we'll talk about, these properties being operating system and the hardware architecture. And then finally, we have dynamic network techniques that try to diversify or randomize network in some fashion. So as I said, the focus of this talk is going to be on dynamic platform techniques, which dynamically change properties of the computing platform on the fly. And the platform in this case is defined as the hardware architecture of the system, the operating system, or the machine instance, or some combination of them. And I'll provide 3 examples of techniques that have been proposed in the literature. Of course, there are many more. This is one example, server rotation techniques. In this case, you have a number of servers, all with the same configuration. Now, one of them is active at each time. You serve the users with that one active platform. And then the other ones that are down, you clean them up and wipe them into a pristine state. Another dynamic platform techniques are migration-based platform diversity techniques, where they allow you to migrate an application from one operating system, one platform, into a different operating system, different hardware architecture on the fly. And they use some tricks, compiler-based checkpointing, virtual machines, and so on. The details are not important for this talk, so skip those. But the main point of it is that they change the hardware, the operating system. For example, here from FreeBSD to Debian. And yet another example of dynamic platform techniques are multivariant execution techniques. Here's, again, one example of them. It's called the reverse stack technique, where you have 2 variants, one with the stack growing in the right direction, the other one with stack growing backwards, and then you compare the results. And the idea is that if there is code injection or attack against one variant, the other variant can be used to detect that type of attack. Now, in our evaluation of dynamic platform techniques, we have realized that there are really 4 fundamental features that these techniques provide, some combination of. The first one is diversity, whether or not actually the properties of the platform changes. And if you think about the examples that I gave, The migration-based platform diversity technique actually does provide diversity because the operating system changes in that case, whereas the server rotation technique does not because all of the machines have the same configuration. The second feature is multi-instance, whether or not multiple instances of the platform run at the same time. And going back to those examples, the multivariant execution technique, the reverse stack technique, actually does provide multi-instance, but the migration-based technique does not because one platform is active at any time in this case. The next feature is limited duration, whether or not one task can run on multiple platforms. So if the technique supports limited duration, it means that it can pause a task, move the task to a different configuration, and then resume the task. On the other hand, if it is extended duration, it means that it has to finish the task before it can change the platform. So in this case, the migration-based technique does provide limited duration, whereas the server rotation technique does not because it has to finish on one server before it can move to the other one. And last but not least, we have the cleanup feature, which means whether or not we wipe inactive platforms into their pristine state. And in this case, the server rotation technique does provide cleanup, whereas the multivariant execution technique does not. And if you look at the techniques that have been proposed in the literature, they really provide different subsets of these features. Here's a list of techniques that have been studied or proposed and the features that they provide. And as you can see, certain features are very common, very popular. For example, diversity, many of them actually do provide diversity. Whereas other features like cleanup are very rare. So 2 of them provide cleanup. Now, the main questions remain relatively understudied and unanswered. So what are the impacts of these techniques? What types of attacks do they protect against? Are the impacts straightforward and intuitive as many of the studies claim? For example, they always claim that more diversity is better. Is that the case? What types of attacks do they protect against? How do we compare different features from these techniques? Is it better to have cleanup or is it better to have multiple instances? Because these features are costly. Maybe we cannot provide all of them. So which one is better to provide? And the goal in this effort was to be able to answer these questions using quantitative evaluation. So we have set up experiments with one of these dynamic platform techniques. And I'll present the results here. So for the rest of the talk, I'll describe the experiment that we have set up, the results that we have had from our experiments, and then we'll explain some of the effects that can be observed in dynamic platforms using analytics, and then we try to verify and validate our results using modeling and simulation, and then I'll describe some of the lessons learned that we've had. So for the experiment, we have used one of these techniques. It's called Talent. It's a migration-based platform diversity technique. It allows an application to migrate to a different operating system and different hardware architecture. It natively supports limited duration and diversity, but it doesn't natively have cleanup and multi-instance, but we have augmented it with those features to be able to experiment with it. The main reason for selecting Talent was its availability of code to us because we developed it. We don't argue that it's a particularly good technique or a bad technique. We just used it here in order to be able to study different effects that are going on. And for the experiment, we have developed a sample application that was written in C. The backend was C. The front end was a graphical user interface. If you're curious, the application was an attestation server, but the details of it are unimportant for this talk. And on our testbed, we have 5 different platforms with 5 different operating systems: FreeBSD, Gentoo, CentOS, Fedora, and Debian, running on top of either Intel 32-bit CPU or AMD 64-bit. And we have 2 exploits on our testbed that are effective against 3 of these platforms. The first one is effective against Gentoo. The second one is effective against Fedora and CentOS. Now, the defender's goal here is to select a subset of these platforms and then randomly migrate across them in order to evade attacks. And the migration happens randomly between every 40 and 60 seconds. So roughly every minute we migrate to a new platform. On the other hand, the attacker's goal is to launch exploits and compromise the system. So in this case, we launch exploits at random times on our testbed. And the goal of the attacker, is to compromise the system for some long period of time. So if the system is running on top of the compromised platform for some long time, the attacker wins. In this case, we parameterize that as capital T, which is the attacker's goal. So if we have these long runs of compromised platform, the attacker wins. If, on the other hand, we disrupt that and we have clean platforms in between, the attacker doesn't win. So here you can see that platforms 1, 2, and 5 are deployed, and platforms 2 and 5 are actually vulnerable to the exploits. So when they're launched, these platforms go down, and they're compromised every time we are running on top of them. And the defender, in this case, doesn't know which platform is vulnerable, which one is not. And this is a realistic assumption, because otherwise they could have just run the non-vulnerable platforms. So we are interested to see the impacts of this technique. So we really want to see the probability of success for the attacker, the portion of time or trials that the attacker wins, plotted against the attacker's goal. So how much time the attacker needs in order for them to achieve their goal, or how much time the attack needs to succeed. And we want to plot that for different number of platforms, 2 to 5 platforms, and 1 platform is the baseline. We'd never change that. So I have to tell you that the day that we were expecting to have these results from the testbed, somebody actually called my office and said, Hamed, something really bad must have happened, because the results make no sense, because this is what they look like. And at the first look, this is really surprising. You know, why do the results look like that? Why the curves are shaped like that? What is going on with, you know, the steps that you're seeing? And there are a number of peculiarities that are going on in the results. So let's look at what those are. First of all, the results for one platform, the curve is very different than the other one, and it looks like to be a straight line after t equals 100 seconds. Another weirdness in the results is that more platforms is not always better. As you can see here, in this part of the graph, 5 platforms is actually much worse than 2 platforms. The attacker has more chance of success with 5 platforms in this case. There are also a number of downward steps, as you can see, at t equals 60 seconds, 120 seconds, 180 seconds, and so on. So something must be going on there. So we tried to explain what we are observing in the results by explaining different effects that are going on based on different features that these techniques provide, one by one, to see if we can explain what we are seeing here. Now, the first effect that we have explained is the limited duration effect. And if you think about it, if the attacker needs t seconds in order to compromise the system, and the platform duration, the amount of time we are spending on one platform, is d, if the attacker starts late, they never have enough time to compromise the system for t seconds. So by definition, they lose if they start late during that duration. On the other hand, if they start early, they can win. So the probability of them winning is really proportional to this ratio of t and d. And that's what we are seeing in this curve. This is exactly the curve for limited duration effect. And that explains the general downward trend for probability of success for the attacker. It also counterintuitively explains the results that we are seeing for one platform. Now, in the case of one platform, the platform never changes, right? We are just running on one. But the entire trial has limited duration. So if the attacker starts late enough during that trial, they never have enough time to compromise the system for larger than t. And that's why the one platform results approximate this straight line curve. The other effect that we are observing is diversity. And if you think about it, if the attacker needs slightly more than 2 platforms, more than the duration of more than the duration of one platform to win, if T is slightly larger than D, the attacker at least needs 2 platforms for them to win because there is not enough time during one platform to compromise the system. Or if they need slightly more than duration of 2 platforms, they at least need 3 platforms for them to win. And that's what we are seeing in these downward steps. So if the attacker's goal is very small, they only need 1 platform to win. And that probability is 3/5 because 3 of our 5 platforms are vulnerable. If they need 2 platforms, that probability is 3/5 times what is left. We don't repeat the platforms, so 4 platforms are left, 2 of them are vulnerable, so times 2/4. And then so on. That's why we are seeing these downward steps in the results, because these are the thresholds where the attacker's goal passed the duration of 1 platform, 2 platforms, 3 platforms, so on. The other effect that we observed was using multi-instance. So we reran the experiments, in this case, using 3 platforms, and we plotted the results while we have a single instance system where just 1 platform is active at a time, 1 out of 3. And also a multi-instance case where all 3 platforms are active and we are voting on the results. And here are the curves. As you can see, this is again very counterintuitive. Multiple platforms is worse in this case, at this part of the chart. And this initially didn't make any sense, but if you do the math, it actually adds up. So the probability of 1 platform being vulnerable when we are running just 1 platform, if you do the math, is 0.3. But if we are running multiple platforms, the probability of 2 or more of them being vulnerable or being compromised is actually 0.7. And this makes sense because the majority of our platforms are vulnerable, 3 out of 5. So the more platforms we pick from that pool, the higher chance we have in selecting a vulnerable platform. That's why we see that in the multi-instance case, at least for short duration attacks, the probability of compromise is actually higher than single instance case. So this is one of the takeaways, that if the majority of platforms are vulnerable, more platforms is actually worse. And lastly, we have looked at the cleanup effect. And cleanup, we have plotted it for 3 platforms without cleanup and with cleanup. Of course, cleanup is trivial if the attack doesn't repeat, because if it is a one-shot attack, the attacker compromises that platform, we are cleaning every other platform, so as soon as we migrate away, we are on a clean platform, and it will never be compromised again. But if the attack repeats, then this probability is non-trivial. And we have plotted here attacks repeating with mean time between attacks of 20 seconds, 40 seconds, and 60 seconds. Of course, if the attack repeats faster, we have more chance of compromise. But as you can observe, cleanup actually has a significant benefit, because for attacker durations that are longer than the duration of 1 platform, cleanup actually prevents those types of attacks, because the attacker never gets to compromise more than 1 platform, because every other platform is being cleaned. So for durations of more than 60 seconds, the probability of compromise goes to 0. This is again a rather surprising finding, that cleanup has a significant impact on the security of these systems. So we have explained these effects, but here's a dilemma. How do we know that we have explained everything? What if there are major effects that we have missed? How do we know that this is a close approximation of dynamic platforms? In order to answer that question, we have developed a generalized model of dynamic platforms using the effects that we have observed. And these generalized models are built using Markov chains, but essentially they capture all these 4 effects that we have explained: limited duration, diversity, multi-instance, and cleanup. And the idea here is that, okay, so we have run some testbed experiments. We tried to explain some of the effects. If we simulate those effects and get results that are close to the testbed experiments, we have at least explained the majority of the effects. If not, if we observe something completely different, we have missed something. So that's exactly what we have done. And I don't go into the details of the Markov models, but you can find that in the paper. We have actually developed a model for different assumptions that you can make about the attacker, different payoff models for the attacker, and so on. So there are really 4 different Markov models that we have developed. But by simulating that generalized model, here are the results that we get. So as you can see, the colored lines are the simulation, and the dotted lines are the testbed results that I've repeated here. And they match fairly closely. So that assures us that we have at least explained the major effects that are going on. Maybe we have missed some minor effect or minor side effect, but we have captured the main effects. And there are also 2 insights that we can observe, both from the simulation results and from the testbed experiments. And if you want to remember anything from this presentation, remember this slide. And that is that if the attacker goal, if the attack requirement is very small compared to the duration of one platform, or if this ratio goes to 0, the attacker wins if and only if any of the platforms is vulnerable. This is because if any platform is vulnerable, the attack requires a short amount of time, they can succeed on that platform and be done. And in this case, actually, diversity hurts security, because by diversifying the systems, we are giving the attacker more options for them to succeed. On the other hand, if this ratio goes to infinity, or the attacker requirement, or the attack requirement, is longer than the duration of one platform, much larger than that, the attacker wins if and only if all of the platforms are vulnerable, because they cannot win with just one platform or 2, they have to compromise all of them. And in this case, diversity actually improves security. So diversity is only helpful for long duration of attacks compared to the duration on one platform. And this was one of our findings. We also had a number of lessons learned during this project that I'll go through briefly. First of all, many of the effects that we observe in reality when we run these techniques are very counterintuitive. You initially don't think that more diversity can hurt the system, but as it is the case, it can for some attack models. And experiments on testbed can actually uncover some of these counterintuitive effects. And moreover, threat models are crucial in deploying pretty much any security defense, but it is also the case for dynamic platforms, because for short duration attacks, things like diversity can hurt security, whereas for longer duration attacks, it can actually be helpful. So we have to be mindful of what the threat model is, what types of attacks we are worried about when we are deploying these techniques. Another finding was that cleanup can actually be very effective, and more techniques must deploy or must support cleanup feature in order to provide more benefit. And last but not least is that experiments, analytic evaluation, and modeling and simulation can be powerful tools in measuring security of different security mechanisms. And keep in mind that many of the assumptions and many of the intuitive thinking that we have may be proven wrong when you actually experiment with these techniques. So to conclude, we have provided the first quantitative evaluation of dynamic platform techniques, and many of the counterintuitive results allowed us to explain some of the features that are going on, some of the effects that are going on. And we verified and validated our results using modeling and simulation, and we enumerated the number of lessons learned. I'd like to also thank the following individuals for contributing to this project. Now I'd like to take questions.
Okay, let's start the speakers. Questions? There's a question, Mark.
Thank you. So first of all, this is really cool work. So I really find it really interesting. And I'm going to play devil's advocate, right? So don't take this negatively. I think your conclusion, which says diversity only pays off if you have long time duration attack, That's true, but if and only if you have no detection method in place. Because, of course, I guess that supposes that you have to do many times the attack in order to find one that will eventually work, right? So I think that's a very critical missing part in neural modeling. And, and I think that would be easy to add, but not by playing with Markov graph, because they might be very annoying to write and follow up the logic. Because what you do basically is what people have done in dependability with stochastic Petri nets and calculating mean time before failure, mean time to failure, and so on and so forth, which is, so I really hope the next paper next year will be with these computing of costs for the attacker and risk of being detected on top of that, because that's really cool.
Sure.
Am I right in making that assumption?
Yes, that's very true. We, in this particular piece of the work, we make the weakest assumption about the defender. We assume that there is no detection capability, they don't know anything about the vulnerability, and they don't learn from the system. We have follow-on work. One piece of it will be published in the upcoming moving target defense workshop, but yeah, you're right. The model can be richer to explain for secondary effects and more strategy and more detection capabilities.
I have a question.
Sure.
When you have the length, the T length of the attack, what kind of attacks do you have in mind? Because most of the attacks they are, against a platform run in the, in the span of milliseconds, which would make all this diversity completely irrelevant.
Right.
So, and the only one I could think about was brute forcing some, a return address that you have to try continuously. But in that case, switching platform simply resets the time. It doesn't really.
So, in particular, that's why we actually call it attacker's goal, not necessarily the duration of attack. But this is the time where the attacker needs in order to achieve some meaningful effect. So think of it in terms of exfiltration attacks. Now, the exploit itself may work in terms of milliseconds, but then for me to succeed, I need some long duration to be able to exfiltrate that data. Or if it is a process control system, it has to go down for some period of time in order for me to achieve the malicious effect that I want. So, if it goes, let's say it's, command and control of nuclear power plant. If it goes down for more than 5 minutes, then something bad happens. So my goal would be to disrupt it for more than 5 minutes in order to achieve that goal. If it is down for 100 milliseconds, it may not achieve the desired goal.
Okay, but I want to understand this. Okay, I'll take your exfiltration example. So my exploit in 1 millisecond is able to execute, some shellcode within your server that opens a file and starts sending some important information out. But if really you checkpoint the application and you move it to a different server, that file will still be open. It will still be sending out the information, right? Right.
So
close the problem.
Correct. Yeah. This the assumption about diversity that we are making in this work, and also it is made in general, is that the attack works against some platforms and not the other ones. If the attack constantly works against every platform, or if diversity is at a different layer than the attack, of course this wouldn't work.
So to answer to your point, I think that my question is more generally, what is really the problem, the real world problem that you're trying to solve? What is a real attack that would have that length and that will not survive diversity? Right.
First of all, we are not proposing a diversity technique here. Our goal was to evaluate these techniques. Okay. But yeah, the goal, there are different attacker payoff models that you can think of. And I'll encourage you to read the paper because we enumerate all of them. But there are binary models where if the attacker is on the system for some period of time, then all of a sudden they win completely. They achieve some unreversible impact, let's say, meltdown of the power plant, and then they have everything. And there are attacker models where they're proportional. So the more the attacker is on the system, the more damage they can do. Exfiltration is an example. The more I am on one system, the more information I can exfiltrate. And based on which one we are talking about, there are, real-world examples of attacks that have those models.
Other questions?
How did you estimate the probabilities you fed into your Markovian models?
Oh, that's a very good question. Actually, we don't. We don't have any reason to believe that numbers are realistic, we just parameterize them in our evaluation. And that's why the generalized models are completely parameterized. We just try to explain different effects that are going on with these models, and with these dynamic platform techniques. So 40 to 60 seconds may be realistic for the platform duration. It may not be. If you believe that those are not the right numbers, you can plug whatever numbers into our model. But we parameterize those numbers into the generalized model. We don't believe that we don't argue whether or not they're realistic.
Another question?
Hello. First of all, thank you. This is very interesting and very counterintuitive. Is data available? How linear is this tail? Because, going back to the real world problem, technically speaking, if I slow down the response, I have a defense on the defenseless system because my system expires before it actually is completed. So there is actually a very interesting side effect, very practical to that.
So your question is how linear is the effect?
How linear is the tail after, if you go back to the graph? Is the data available? Is this something you are willing to share?
Yeah. Well, the data is available. It is presented in the paper, but we just evaluated it up to 300 seconds. We don't know how linear it is afterwards.
This part, how linear is it after 100 seconds?
So, I mean, there are error numbers in the paper, but it's not really linear, but it approximates linear.
One last question.
So your parameterized models, do you have any thoughts for how you might be able to estimate the values of those parameters?
Yeah, I mean, the only approach would be to look at the attacks that you're really worried about and evaluate how fast they can achieve their goal, and actually run those exploits or run those attacks and try to collect parameters that way.
All right, thanks for speaking.